does. Thank you, Adam, and thank you, Ben, for moderating. And it's my turn to take over the baton from Ben on the moderating side.
Yay. So thanks all very much. I will head over to the other track and see you all soon. Thank you. Bye-bye.
All right, and for those of you who are still on the call, we have our next session coming up in about 10 minutes. That will be Daniel presenting. I will see if I can share my GroupBy slides here, if you just hang on. There we go. And then I am going to mute myself for just a little bit here and wait for Daniel to enter the session. So go take a break, stretch your legs, get some fresh air, grab another cup of coffee, and let's get ready for the next part of GroupBy. All right, so we are still on a short break. While we're waiting for our next speaker, I just want to go through our code of conduct. GroupBy is a harassment-free event, and it is meant for everyone, regardless of who you are, what sexual orientation, identity, expression. GroupBy is for everyone. And I think I can summarize this slide in one sentence that I've stolen from our previous moderator and the Data Growland event, which is be excellent to each other. So make sure that you read this. If you don't behave, I will kick you out. So just make sure that this is an event that everyone can enjoy. I also want to say thank you to our sponsors. We have Redgate and SolarWinds, who are the core sponsors here of GroupBy. We also have SQL Solutions Group and Minionware, who presented a session yesterday. So make sure you go and check out the recording once that's available. So thank you to our sponsors. Otherwise, we wouldn't be able to be here today and learn from all of these great speakers. So I am going to quickly mute myself again, just to make sure that we are still here. We will be presenting shortly. Just stick around.
What's up, everyone?
Yo, hello, Daniel.
Did you wait for me?
I was waiting for you. Yes. While we were waiting, we went through the code of conduct and the sponsors to just say thank you to all the great people who make this event possible, and to make sure that people are excellent to each other.
Fantastic. So we got that out of the way. So my speaker that I was moderating on the other track ran over a little, or was about to, so I had to forcibly eject myself.
Yes, we are waiting for you in this track, so I'm glad you were able to, sneak out of that session.
Awesome. So I'm just gonna make myself. Oh, I am the co-host already. So let me see if I can take over the screen sharing. Where does that happen? Here it is.
I'll click on stop share on my side at least.
This is my slide deck, same as the other slide deck.
Perfect.
Awesome.
All right, so I think we're right on time. So if you're ready to go, Daniel, I'll let you introduce yourself and take it away.
Yeah. And so we've spoken about the code of conduct. Thank you, Katrina. I'm Daniel. I'm here to talk about ordering. I'm specifically a very ordered person. I want things in the right order, the first things first, and there's a structure and a process for everything. And that's a very particular, let's just say, personality trait that lends itself well to SQL Server optimization. And so I've prepared a presentation which will discuss ordering of data flows in an execution plan. So I'm hoping most of our attendees have at least looked at an execution plan in SQL Server at some point. If you haven't, don't fret, we'll be okay. It's mostly just comic stuff. So ducks aside, this is my Hugo Cornelis slide. Everything I say now will be basically simplifications. So everything is made to suit the presentation. There are some minor differences and depends and maybes all over. You'll have to excuse me, but the general principle is correct. I just don't want to bore you with all the exceptions. Again, if Katrina didn't already mention, thank you so much to all the sponsors. They're not here to call you about your extended car warranty. They're really here just to let you think about them and, have them top of mind if you at some point are going to purchase like a monitoring software or something like that. So without sponsors, no conference, and that's why we're all here. So basics, how data is stored in SQL Server. Everything in SQL Server, like this example table, is stored in pages. And I mean everything with an asterisk. You remember I said about the disclaimer, everything except the transaction log and the file stream, which are special cases. Everything else is stored in pages in SQL Server. So a page is a logical storage unit somewhere in your database file, which is 8 kilobytes in size. A page can contain rows. About pages in SQL Server is that they link to each other. So every page contains a tiny little metadata header, and in that metadata header, there's a pointer to the next page and a pointer to the previous page. That way you can traverse the pages. You can start off with row number 1, row number 2, row number 3, and so on. And when you finished your page, there's a pointer. So you can find the next page, and then you can continue reading from that page. And so you can see how if you do select star from a table, what you're basically doing is you're finding the first page of that table and you're traversing it. And then you're finding the next page and traversing it. And so that asterisk determines the order in which you get your data back from that select query. Moving on, every table in SQL Server, every row stored table with a clustered index, the clustered index is the table structure. So it's not like I believe in Oracle or in Postgre, where you have a table and then you have a clustered index next to it, sort of, and the table is just a heap. If you assign a clustered index to a SQL Server table, that clustered index is the actual table. So the data in the table is stored in order of your index key for the clustered index. In our example, we have a clustering index key that is called ID. That is our identity column. So we've chosen to define our clustered index on the ID column, which means everything in the table is stored and sorted by that ID column. And I basically just went through this, but I just want to show you my ducks. I didn't draw these myself. I bought them on a site. and so you can see the 1, the 2, the 3, and the 4, and so on. Those are, you think of those as the index key in this case. The ducks are the entire row, and the numbers are the index keys. How about a heap? Because you've all seen it. People just, create table and you don't assign a clustered index, you don't assign an index or anything. A table without a clustered index in SQL Server is called a heap. And a heap is exactly what it sounds like. It's a bucket where you've just dumped everything down, and it doesn't matter in what order it is, which also reflects on if you do a select star on that table. If you select star on a heap, everything comes out basically in the order we found it in the table. You can't be sure of anything. How about non-clustered indexes? A non-clustered index is a subset of a clustered index. So say a clustered index will sort the data on the index key, but at the leaf level of this B tree structure, at the very leaf level, you have all of the data from the row. So because I mentioned earlier, the clustered index is the entire table. The leaf level needs to contain everything that you actually store in this on each and every row. A non-clustered index, however, is much, much more tiny, or can be, because it only includes the index keys, and if you choose to explicitly include other columns. So non-clustered index can have a different index key by which it's ordered, and it contains a pointer to the clustering key, which is there. So in this case, for instance, with our ducks, I've chosen to make a clustered index key, a non-clustered index key on the name. So we get a phone book-like ordering of our ducks instead of the ID number. But in order to find the clustered row, the base table row for each duck, we also need to have the clustering key. So a non-clustered index will always contain the index key, any included columns you have, and a pointer that points back to the clustered index. So to the left, you have a clustered index. To the right, you have a non-clustered index. And you can see right away that the non-clustered index fits a lot more data in it because we don't have information like birth date or role. We just haven't included those columns. We've just indexed on first name, and we've included the clustering key, the ID. So touching on something that we discussed before, there are two different major ways of accessing data in tables and indexes in SQL Server. There are scans and there are seeks. An index seek is where you can use the index to go directly to an index key. So if you do a clustered index seek, for instance, excuse me, if you do a clustered index seek, you will look up a specific key in the index. In our case, the clustering index key is the ID column. So if you look up a specific ID in the table, you can jump right to that place in the index. It takes you basically 0 milliseconds. It's super, super fast. And that's why you use a seek. A version of the index seek is the range scan, where you start, like before, at a specific index key, and then you scan forward until an end criteria. So in this case, if we want to get all ducks between 5 and 10, you would do an index seek to number 5, and then you would just scan it until you come to 11, which is not between 5 and 10 anymore, and you're done, you're out. And also, this is also a very, very efficient operation. Now imagine if our table had 1 billion ducks, it would take you forever to just look through the entire table, but it's super fast just to go to duck number 5 and find the next 5 ducks, and you're done. This is what it looks like in a table structure. You go directly to row number 5, and then you just keep going until you're at number 10, and you're out. Index scans, on the other hand, is when you need to look through the entire table. You can't really use the index, so you just look through the entire table. You won't notice an index scan if you have 10, 15, 20, 100 rows, even 10,000 rows. It'll be hardly noticeable because it's so little data. But if you have like a data warehouse or 1 billion rows or something, I'm curious to see how much space 1 billion ducks would take. An index scan will take absolutely forever because you need to waltz through those gigabytes of data on disk. At worst case, you won't have them in memory even, so you'll have to actually read on the disk. So the non-clustered index starts at the very first page and it traverses through each and every page. If you just do select star from a table, that's what you're getting. A non-clustered index scan is the same thing, but it just traverses the non-clustered index. In this case, if we're just selecting ID and first name, those two columns can be found in our non-clustered index, and we don't even need to look in the clustered table. But you'll notice that when we select from the non-clustered index, the non-clustered index is stored by name first. So the output of this query will, unless something else happens, be ordered by first name implicitly. And these are my PowerPoint animation skills. Which brings us to the next topic, which is always one of those things that we performance tuners love to talk people to death about. Here's some audience participation. If you were to do a query on a clustered index, for instance, you have the clustered index in the lower end of the screen, where you want ducks between 5 and 10. How would you do that? I don't know how to do audience participation. I'm not going to put up a poll or anything. So I'll just answer the question for you. We would obviously, like we discussed, we would go directly to 5, and then we do a range scan until we reach 10, and we're out. This is an index seek or a range scan, depending on what you call it. How about this? pick up the chat window here. Anyone have a good guess how you would solve this? I wonder if people are typing furiously or just sipping tea and answering. Same way, David says. Yes. And why is that? Because we can compute the square root of 25 and the square root of 100, and we reach the values 5 and 10. So we can solve it with a range scan, right? Same idea. How about this one? How many think it's the same? David says scan. Damir says table scan. Damir's cheating because he knows. Right. So the problem here is there's no index on ID to the power of 2. So you would need to look through the entire table, evaluate every row. Does this row match? Does this row match? Does this row match? So 1 raised to the power of 2 is 1, which is clearly not between 25 and 100. 2 raised to the power of 2, still no, still no, still no. And this is how I do PowerPoint animations. 5 raised to the power of 2 is 25. So we'll include this row. And same with number 6, number 7, and so on. And when we get to 11, we realize that 11 raised to the power of 121 is 121, which is not between 25 and 100. And you and I would stop here, but SQL Server isn't that clever, because maybe, just maybe, 12 to the power of 2 might be between 25 and 100, but it isn't. And so this query will just go until we either get a data type overflow or we've completed scanning the entire table. So the idea here is to avoid these kinds of table scans, which are terribly expensive. You want to rewrite this query. So instead of instead of ID to the power of 2 between 25 and 100, you would want to do something like this that we looked at before, depending on your math skills and where you come from. Other cases that you will see here are related to data type conversions. I've seen plenty of cases where you convert a date column to a varchar and then compare it to a varchar. And what you should do instead is convert the varchar constant to a date type and then compare it to the date. So that's about sargeability. If you know sargeability, half your performance tuning job is done. I would say 60% of all the performance tuning at some point comes down to sargeability, or perhaps just a non-clustered index column. Yes. Table scans are clustered index scans for tables without clustered indexes. So basically they're heap scans, but table scans sounded nicer, I guess. And yes, as Alexander says, any function on a column will prevent the usage of an index. Whereas you could do the reverse function on the constant instead and use the index and make it surrogable. How about key lookups? Key lookups are these sort of needle point lookups in a clustered table. They're called RID lookups, row ID lookups for heaps, but all you need to keep track of is really key lookups, because no one should use heaps. So a key lookup is practical when you, where's that slide? Yes, here's an example query. Let's say we select ID, first name, and birth date from ducks, and we order it by first name. The practical way to solve this, because we have a non-clustered index on first name, the sorting is already done for us. The hard work has already been completed by building the index. There's just a catch. We don't have the birth date. Birth date is not an included column in the index. So what we do instead is we use the non-clustered index to scan by first name. It's ordered. We have the data the way we want to present it. And then for each and every row in the non-clustered index that we get back, we do a little lookup in the clustered index. Right, so we have Chuck. Chuck is number 4. what is the birth date of number 4? That's a key lookup. It's super fast. The key lookup is absolutely a small fraction of a millisecond, but you can figure out what happens if you have a billion of them. So key lookups are your friends and your enemy at the same time, just, depending on where they appear. Same for Daffy. What is Daffy's birth date? Same for Daisy. What's her birth date? And so on and so on. And I think this animation goes on for some time. So the way to fix key lookups, if you have the disk space and the patience, is to include those columns. You can, if you look at a non-clustered index, you have the first name, which is the ordering column, and you have the included ID of the clustered index, which points us back to the actual row. We need that. What you can also do is you can include a column that is not per se part of the index order, but it's there just for lookups. So it solves our problem that we had just now, that if you select ID, first name, and birth date, and you want to order those by first name, you can have the birth date in the non-clustered index. So you won't have to do the key lookup because the data is already there. Be aware that if you change the birth date of any duck, which I guess is kind of hard, but it could be a typo, SQL Server needs to update the clustered index and the non-clustered index now. So there are no free lunches in this world, including non-clustered index. So if you include a column, it's faster for select queries, but all your updates and deletes will, or updates and inserts will potentially suffer. All right, so which brings me to the next chapter, sorting. If you select ID, first name, and role from ducks, order by ID, you will remember that our clustered index is already ordered by ID, so we can just get everything out. We don't need to do anything. If you hover over the query plan icon in Management Studio, it will, if you look at the very bottom of the yellow pop-up window, it says ordered equals true, which means just that it will maintain the index order where as the information is stored in the index. So the data is already ordered, which is perfect because sorts are expensive. This is the way you want to go. But what happens if we order this information by first name? Well, we could use the non-clustered index, but we don't have the role column in the non-clustered index. So SQL Server, in its infinite wisdom, decides to use the clustered index instead because it's the most practical one. This comes at a cost because we need to select data from the clustered index, and then we need to sort that data. And sorting is one of those expensive operations in SQL Server, and I'm going to show you why. Imagine if you have like two pipes. The red pipe is where the ducks come in. And when I drew this slide deck many years ago, I was kind of asleep on the job. So the data comes from left to right, as opposed to from right to left in the query plan. But you can think of it as watching from the inside and out in SQL Server. But the data stream from the clustered index comes in the red pipe, and you want to sort it to get it out to the green pipe. Now imagine if you hold a deck of playing cards in your hands, how would you go about sorting those cards, right? Can you do it in just one hand and just give me the first card and then find the second card and give me that card? No, you need to store this information somewhere. This could be your RAM memory. It could, worst case, be your temp DB, depending on how much this information is and how much space you have. Do you know what is more expensive than sorting in SQL Server? No. SQL Server licensing? I can't think of anything, actually. Sorting or Oracle? Very well, very well. Yes, sorting in Oracle is yeah, let's not go there even. So what I'm going to do is I'm going to spill everything that I want to sort before I do anything. And why? Well, because the first row to exit, the first row that I'm going to put in the green pipe might be the last row out of the input, right? So you don't know that before you've started. So we need to put all of these ducks in our temporary storage space, which could be our memory, if we have plenty of memory, or we would have to spill it to tempdb. Then sort happens. If you develop in traditional programming languages, you know there's bubble sort, and there's this sort and that sort, and there are a million different sort algorithms. And I believe that SQL Server has a couple of those to choose between. We're not going to get into the internals of how that happens. Just think of it like a cartoon cloud where stuff happens. When all is said and done, these ducks are sorted, and we can start pushing them out into the green pipe and returning them to the user. There was something I was going to say here. I'll probably get back to that. Yeah. Oh yeah. So did you notice something? Because we need the entire data set from the red pipe before we can even start sorting, or actually before we can start returning data, this becomes like a blocking operation in the query plan. And I don't mean blocking in terms of placing a lock on anything. It's not like that. What it does is, in a streaming flow of data, where data just flows from the lower right corner of your execution plan to the select in the upper left, everything stops. So it bunches up. You get all of these ducks just stuffed up in a memory allocation. And then everything needs to be sorted. And then you can start returning them to the client. So the client needs to wait until everything is sorted, not just until the first row sort of is processed or anything. This is called a blocking operation. And it also, storing these ducks here, invokes a memory grant. So you will need to allocate memory for this operation to run, which is, if you have large amounts of data, that's going to be less than desirable. Moving on, window functions. When I learned window functions, I thought they were like T-SQL 2.0, because you have this incredible, powerful query language, and then someone like Itzik comes and says, hey, have you seen window functions? And a whole new world opens up to you. And that's definitely what happened with window functions for me. Window functions are amazing, but you also need to understand how they work, and they can't run on magic alone. They need some prerequisites to function. One of them is ordering. So think of this. If you have a set of ducks and you want to order them, you want to give each duck a row number. And the row number is ordered by first name. And as a tiebreaker, in case multiple ducks have the same name, you want to have ID. Or another way to express a similar question, you want to introduce a partition. You want to reset the row number for every time the first name changes, right? So you want to basically find duplicate ducks. If Angus has 3 rows, you want to find Angus 1, Angus 2, Angus 3. And how we do that is we partition the ducks by first name. And then for each first name, we sort them by ID, right? This is what that looks like if you remember the red and green pipe analogy. If you think of the data coming from left to right, you just look at them, you define a window, which in our case, in the query language, we call those partitions. Every time there's a new duck, a new window or partition, in this case, a new first name, we set a little bit to 1. That signals this is the start of a new partition. So every time Angus, the first Angus that shows up is a 1. The first, I don't know what they were all called. The first Bart or whatever is also a 1. So that little bit column signals that, and this is the start of a new partition. And so once we've defined this bit column, which we can call a segment, because it's the start of every new segment of ducks, we can start counting up 1, 2, 3 until we hit a new segment, at which point the counter resets. So it's 1, 2, 3, and so on and so on. And this is what it looks like in the query plan. So if you look from the right to the left, you're doing an index scan, you're returning all those ducks, you're segmenting them. So you're looking for changes in the first name column. If this first name is not the same as the last first name, we set the segment bit to 1. Then we move on to the sequence project or sequence project. I think it's sequence project operator. And sequence project in this case is pretty stupid. It just adds 1 to our counter column. It just adds a 1 for every new row, except when the segment bit is set to 1, in which case it just resets. So segment will keep track of the segments. It'll just set a 1 when there's a new segment, like a new first name. And the sequence project will just keep the counter clocking up until it sees that it's a new segment. Now, those of you with a sharp vision have noticed that there are some prerequisites that we filled here. The data is already sorted by first name and ID, right? Because if it isn't, if you don't have a non-clustered index, you will need to sort that data first in order to facilitate the row number function. And again, we've already discussed the sort operation. How are we on time? Almost half an hour.
We are good on time. I think you have 15 minutes left.
Perfect. I have like 600 more slides. No, just kidding. So aggregation is something we do as data professionals. And this is the way we would always want to aggregate stuff. There are two ways basically to aggregate information in SQL Server, or at least in row store. We have stream aggregates, which are prerequisite on the data arriving in a stream. So what we have here is a bunch of ducks. They're already sorted. They're all in line. We're just tallying them up. So think of this as just a count star, right? Or a first name, comma, count star. We, from left to right, this duck is, we have 1 duck, 2 ducks, 3 ducks, and so on. We have 14 ducks. And after 15 ducks, a new first name appears. So we just deliver 1 row from this operation, and that's Angus, comma, count equals 15. And then we see that there's a new first name, and then we start counting up that again. So this is perfect. Note that it says sorted input, because just like the row number function, it requires the data to already be sorted. That can be the index, that could be a sort operator. If that isn't possible, there's something called a hash match aggregate. And you'll see this a lot in SQL Server because the world isn't perfect and sorting is supremely expensive, unless you're on Oracle, in which case it's hilariously expensive. So think of an unsorted input, or just not sorted the way you want it to. In order to, say, compute a count star based on a first name or whatever, you would have to know what you're dealing with first, right? Because the rows aren't ordered, and there might be an Angus at the very end of your stream, which you don't know of yet. So what we do is we place all of these in buckets. Think of them as actual physical buckets on your floor in your office room. The difference is we hash these keys, so it takes less space to store, and it's more efficient from a computational standpoint. So we place different types of ducks, different first names in respective buckets. We do a little hash algorithm on the first name, and that hash algorithm gives us like a binary value that defines which bucket we place these respective ducks in. But as with the sort operator, note that we can't start returning rows to the green pipe until we've exhausted everything. Here's another simplification. There are ways you can do a hash match without actually consuming the entire input set. I'm not going to cover that because this is a level 100 session. So we put all of these ducks in their buckets, and now we can, 1 bucket at a time, 1 value for each bucket at a time, start returning these. So we have 15 A's, we have 7 C's, and we have 12 B's. Did you notice it? I'll do it again. 15 A's, 12 Bs, and 7 Cs. So the problem here is because we're processing these hash buckets, the data isn't ordered anymore, or at least it's not ordered by first name anymore. It's ordered by the hash value. So we're going through the hash buckets, right? So for all practical purposes, this data isn't ordered anymore. It's unordered. It's one row per first name, but it's not sorted by first name anymore. So if you do anything with a hash match or hash join, ordering is lost for all practical purposes. This is what a stream aggregate looks like in a query plan. You can see that we're scanning the index scan, stream aggregate, and just returning the data. No sorts, no memory grants, nothing holding up anything. This is just efficiency, 0 bytes of memory grant. It's just super fast. The same thing can be said for just the select. Distinct if that distinct follows an index order, because the only difference between a select distinct and a select count big GroupBy is just that there's no count really. The query is the same. You need to order and aggregate the data the same way. How about if we select birth date and see how many people are born on each birth date? Well, we don't have a covering index, so we would have to use the hash match. In the same vein, you could do a stream aggregate, and SQL Server will do that sometimes, and it will sort the data to fit the stream aggregate. SQL Server has a built-in optimizer that will sort of evaluate based on the characteristics of the data and the size and sort of the cardinality, and make a best guess. Because of these two options, the hash match and the sort, they both need a memory grant. They're both blocking, but there you can draw a curve that describes the efficiency of them both, and you want to find sort of the intersection, which one is more efficient for your specific data. And if you want to go really, really deep, Hugo Cornelis has an amazing half-day session, I think, on hash match and nothing but hash match. Anyway, and you can do. This is also something you will see sometimes if you just select distinct by a column. It might do, instead of sort and stream aggregate, it will sort of bake those two together, and it's slightly more efficient because you don't have to pass a lot of information between sort and stream aggregate. It'll do both in the same operator. And that's the sort parenthesis distinct sort operator. So some joins as well, just going through the entire query plan. The simplest join in my book is, and this is if a long time ago I built an Excel macro that would join two sheets of Excel together. And what I did was I sorted those two sheets, and I would go from the top of the left sheet, and for every row in the left sheet, I would just take all of the rows in the right sheet that matched those conditions. That's what the nested loop is. Think of a nested loop as a for each in a traditional procedural language. So for each row in the top input, we collect all of the matching rows from the bottom input. And this typically in a nested loop join, it happens as it does a select. So you could think of, you get one row, one more row from the top input, you do a select in the lower pipe, and you return those rows. So next duck, you do a select from the lower one, and you send those on. And if you noticed, we're not buffering anything, we're not storing anything. What goes in goes out. There's no memory allocation, there's no blocking. So this is in its very simplest form, a for each loop. And this is what it looks like. So in this example, you will do this index seek, which is highly efficient for every row that comes out of this. Merge joins. I gotta say, this is my favorite. The merge join is if you have two data sets that are identically sorted, you can sort of interleave them into each other. And I hope they have the video of this session on the YouTube recording, because that's basically what it is. It interleaves the two result sets into each other. So like a zipper basically on your jacket, you will just interleave all of these rows. And also note that there's no memory grant. There's you don't need to store anything anywhere. You don't need to compute anything. You just join them, send them, pick new rows, send them, and you're on your way, right? And there is an asterisk if one of these inputs needs to be unique, because if they're both non-unique, you need a small memory cache just to store that Cartesian product of joins. This is what a merge join looks like. Remember, these two need to be sorted in the same order. And also, typically, they need to have the exact same data type and everything. So it really, everything, the stars need to align for a merge join to happen. But when it does, it's just blazingly fast. My favorite join. Which brings us to the catch-all join that I like to think of. So hash join works a lot like a hash match. It's actually a hash match variant. It also uses buckets, and I think these pipes are upside down. You should probably think of the build pipe as the top pipe and the other one as the bottom, but never mind. So what we do is we have a build phase where we analyze the incoming ducks from the build probe, the build something. And then we have a probe phase where we pick ducks from the other pipe and say, what hash bucket does this match? And then you match those and send them on the merry way. And the next duck, you match that to its matching hash bucket. You match those together and you send them on their way. And again, you can see the use of buckets. We're storing this data. We need space, which typically happens in RAM, but all too often goes down to tempdb. So again, hash match or hash join is very, very common. It's the absolute go-to for SQL Server. It's you will see it absolutely everywhere because it's if no other tool can solve the job, hash match is typically where SQL Server goes. Which brings us to parallelism. This will be a short one. I just watched Thorsten Strauss speak for 90 minutes on parallelism, and it's nowhere. I'm nowhere that close in this presentation. I'm going to just make it about ordering. Think of a single-threaded flow. You have this ordered data flow of ducks. Looks like this, right? Select star from ducks. If you parallelize this query, you run it in multiple threads. You have multiple readers reading from the same table, and they have this hashing algorithm that determines which thread picks up which duck, basically. And there are, I think, 3 different methods of partitioning stuff between different threads. We don't need to go into those, but suffice it to say, you can't really predict in which way these things are sort of assigned to different threads. But you will notice that different processors may work differently, have different speeds or different availability. So when it comes down to those nanoseconds, you won't preserve the order in the data set. So when you put the data back together, just because you need to return it to your client, it's not ordered anymore. The takeaway is when you do a parallel plan, what comes out of the parallel section of the plan is no longer ordered by any sort of deterministic ordering. It's just ordered by the order in which it exited the function. this is what it looks like. What I just showed you with my amazing PowerPoint animation skills were the gather streams. So you do lots of funky stuff in a parallel zone, and then you need to patch everything together back into a single record set so that we can return it to the client. And when you do that, ordering is pretty much lost. Right, we are 40 minutes into the presentation, and this is the wrap up. This is why you've had to stay awake all of this time. This is why all of this is important. I've taken a typical demo query plan, and I've just added an arrow to tell you how it's ordered. If you look from the top right corner, you can see that we're doing a clustered index scan on a table called route schedule. I know that the clustering index key on that table is schedule ID. Now we're doing group by schedule ID, which means that we can use a stream aggregate. Remember, the stream aggregate is an aggregation where the data is already sorted by the aggregation key. So the ordering is still schedule ID because it's the same going in as going out in a stream aggregate. Now, nested loop, if you remember, is a for each operation. So for every schedule ID, I want to seek a number of months from the months table. And the primary key, the clustering index key in the months table, is the month column. So can anyone in chat tell me what is the order of the data that comes out of the nested loop operation? We have all the time in the world. Not ordered, says Alexander. Is that really it? Any ideas, Damir? Sebastian says schedule ID. Almost, yeah. So the data is going to be ordered by schedule ID and month, remember, because for every schedule ID, we're going to get an ordered set of months, right? Now we do the same thing for report row. The reason for the red little cross here is because it's a Cartesian join. We get all of the report rows for each schedule ID and month, right? So we have an ordering of schedule ID, month, report row. And you can see now how we build this query. Now for every row that we get from this data set, we would want to do an index seek from transactions, which is a fairly big table now. And we want to do that index seek on the index keys account ID and accounting date. And to do that sort of practically, SQL Server decides that it needs to sort this data up here by account ID and start date. I'm not going to go into all the details of what happens here, but basically you can think of we've optimized this stream up here to suit our select down here, because the nested loop, again, as you know, is a for each loop. So for every row that comes out here, we do a query down here, we stream aggregate it, and we put it in a table spool, which is kind of a buffer just to keep it fresh. So we won't have to run the index seek for exactly every row. For some of the rows, nested loop here can just go to the table spool and it'll have the answer from last time. And that's why the ordering matters here. Again, exiting the nested loop, we have the account ID and start date. And now we've selected data from here for a single account, ordering by accounting date, right? So that is our new sort order. And that's basically the takeaway from all of this, is that when you start to look at query plans as a set of ordered data, that everything is basically the ordering of a data stream. It's a whole new perspective, and it will help you design indexes and ordering, and it will help you to optimize your queries to use, for instance, stream aggregates instead of hash matches, or just eliminating sort operations, stuff like that. That's kind of the perspective I wanted to bring you with this presentation. So that was all I had from the presentation. My name's Daniel. You can find me on Twitter. This is my company. This is my blog. Feel free to hit me with any questions or anything that I can help.
Thank you so much. I'll give you a little round of applause. You can't really hear the others, but I'm assuming they're applauding as well. Thank you so much for that.
I enjoy this presentation. It's so much fun, actually. Yeah.
It's fun to watch as well. You've done a great job with your little ducks there, really leaning into the theme.
Yeah, indeed. I just want to keep people awake. Full text indexes, that's a completely different loaf of bread. I'm sorry, I just can't. What I can mention is column store indexes, which you could think of as hashing functions. So again, no particular order. Terry says, on your graphical show plan, worth mentioning the relative percent cost of each step. Yeah, I mean, so what we're trying to do is really to find the most efficient ways to reduce those costs. And you will typically find that the most expensive operations are sorts. Not in this query plan because there are so few rows up here and so many rows down here, but the idea is the same. Yeah, Andy says no one talks about full text indexes. Yeah, I've never seen full text indices in production, but maybe that's just me. Awesome. So who is? I think the next session is in something like 10 minutes.
10 minutes-ish. And I saw Jeff in the chat. Not sure if you have to be promoted or if you're good to go. Hi, Andy.
Hey, good morning. How are you?
Hello there.
Good morning to you.
And good afternoon to you guys, I assume.